The next talk, the next update we'll be seeing in this Flower Monthly is by Madi Beitolani. I'm sorry if I didn't quite
No,
get it.
it's perfect. No worries.
Oh, great. Okay, thanks. And you're probably being very generous, so I do appreciate that too. So Madi, he works at Huawei Canada. And so Huawei obviously is one of these leading big tech firms that are global, doing fantastic stuff ranging from big servers all the way down to really cool phones. But they also do sort of really seminal pieces of ML research. And so he's at one of these institutions there where he is a machine learning research engineer. I also saw that he received a Master's of Science from Queen's University, along with other degrees from other institutions too. Um, and so Mahdi, he works in various domains, including distributed training, federated learning, and parameter efficient fine tuning. And so interestingly, this work kind of brings a lot of those things all together. Um, and so, yeah, I'm fascinated to see what he's been working on and how Flower has enabled an interesting piece of work to be possible. So over to you.
Absolutely. Thank you so much for the introduction, Nick. Thank you guys for having me. Let me just start my share my screen. Perfect. Let's go here. And yeah, can you guys see my screen?
Yes, looks perfect.
Awesome. Thank you so much for the introduction. Thanks for having me here. Hello, everyone. My name is Madi Beitullahi. I'm a research associate here in Huawei, Canada. And today I'm going to present our work named Parametric Feature Transfer, One-Shot Federated Learning with Foundation Models. This is a work done at Huawei, and it was a joint work with my fabulous colleagues that I list here at NOAA's lab here in Montreal, Canada. Today I'm going to be an informal discussion on, let's say, federated learning and foundation models and this area around it. And just want to point out new ideas and direction in that regard. Let me just start my timer. Awesome. So yeah, let's start. Before I start, I have to make an important disclaimer that the work is done. What I want to say and my opinions are expressed do not reflect the organization that I'm affiliated with, and these are just my opinions. So yeah, with that, let's start. So this is the outline for today. First, I'm gonna start with an introduction on federated learning foundation models, and then we're gonna talk about FedPFT, parametric feature transfer at work, and then we're gonna discuss some results, and I'm gonna show you how you can use FedPFT today in using Flower baselines. Awesome. So let's start with the introduction. So I'm pretty sure that everyone's like watching this is we know you know that we are in the era of foundation models, right? Models like GPT-3, Llama, Clip, use them every day. We hear about them all the news, right? And the thing that what is important about them is that these models have huge sizes and they incorporate pre-trained knowledge, right? They've been trained on like internet scale data and they have exceptional performance on downstream tasks. But the important part is that we have to keep in mind that these foundation models should be fine-tuned on downstream tasks to be useful. Let's say for instruction tuning or any classification tasks. And that's where federated learning comes in, like federated learning for foundation models. And in order for us to fine-tune these models for downstream tasks, we have to like some of the data that we want to use for downstream fine-tuning are our user data, and for protecting this privacy, we can utilize federated learning to also leverage the capability of foundation models. So that's where federated learning comes from in order for us to fine-tune these large foundation models. But the thing is that there are a lot of challenges when we utilize federated learning for foundation models. As you probably aware, like traditional FL takes place iteratively over multiple rounds, right? So each client has to send the model to the coordinator after it trains, and then you have to send it to the coordinator and send it back, right? So this multiple iteration and this training and transmitting causes a lot of GPU memory requirements and communication costs. And we're talking about these large foundation models, right? So one approach that I really bring on here and I'm a very advocate of is one-shot federated learning. One-shot federated learning is an approach to address high communication costs of FL by requiring a single communication round. What that means is that like clients only send the model once to the coordinator, and they just receive the updated final global model, right? And like I'm a really big advocate of one-shot FL because not only it solves all of our high communication costs, but also it has very important advantages. One is, for example, easier coordination. Everybody who's works on FL knows that how hard it is to maintain this kind of connection between clients and the server. And that's where like tools like Flower comes in, and they're very good at. It just allows us to coordinate much more easily. And that's where one-shot federated learning solve this problem, right? It's just a one-time connection, and it is much more easier to coordinate. Another thing is that it supports scenarios where multi-round FL is impractical. So let's say in dynamic environments that our data and user behavior is rapidly changing, we want to fast and rapid federated learning process that give us the final model instead of like running these models for days and thousands of rounds. So, and I think it's a very interesting direction that is basically a combination of model merging and federated learning. So it brings federated learning to a new paradigm. But the thing is that one-shot FL is great, but the current methods lack the performance of the multi-round FL counterparts. And we don't have theoretical guarantees because in multi-round FL, we are using the fact that, hey, we run it for a long period of times, and in the end, it's going to converge. So this is very extremely challenging in one-shot FL. And also, one-shot FL doesn't mitigate the GPU memory demands, right? We still have to fine-tune these foundation models on user devices, right? So I talked about like, hey, we need to fine-tune this foundation model, but the thing is that we can also at the same time leverage them, right? Because the pre-trained nature of these foundation models opens up new possibilities for training-free and communication-efficient knowledge sharing among clients in federated learning. And we can leverage the small features of these foundation models as they are without excessive fine-tuning. So the whole summary is that we need to fine-tune these foundation models, but not so much because they already have pre-existing knowledge in them. We can utilize for much more to have a better communication efficiency in the network. So what was our goal in this paper and this project? We wanted a FL method that is practical for pre-trained foundation models. So that's for our goal. The second, we wanted to make it one shot, much more easier coordination. We wanted to make it communication efficient. We wanted to solve the GPU memory demands. And most importantly, that's why we are in FL, we want to make it privacy preservable. So that's where comes in our methods. So in this work, we propose FedPFD, Federated Learning with Parametric Feature Transfer. It's a training-free one-shot FL models that enable foundation models in federated learning. So in this figure, I'm just going to show you the high level. Again, we're just going to go down and show what you're doing. So on the left side, you can see some clients are doing some feature extraction, etc. They're sending some information to a server, and server processes that. So this is a one-shot method, and now I'm going to dive in deep to showcase what I mean by that. So at each client, let's just consider client one. We pass the data set and we extract the features from the foundation model. So this feature extractor is a frozen feature and foundation models that we are extracting the real features from it, right? So we are going to pass the data set for each label. We're going to extract the features of each label of each client to get the real features. And from that, we're going to learn a parametric model. Parametric models are probability distributions that we can learn from any features. So for example, in here, we're using the Gaussian mixture model, mixture of Gaussians, to learn the probability distribution of our real features. Now, we can explain this whole label of this data set towards this probability distribution with its parametrics. So in here, we're going to do the same thing for every client, and we're going to send the parameters of this probability distribution here, which are mu, pi, and sigma, which represents the mean, mixture rates, and the covariance of this probability distribution to the server. Now the server has the probability distribution, and you can utilize that to sample to create synthetic features, right? And from all those clients can combine these synthetic features to train a classifier head. So what we're basically doing is that we're extracting the label of each client and learning a parametric model from them. We're sending it to the server, and by recreating the synthetic features, we can train the classifier head. So what that means is that after that, a user can utilize this classifier head along with the already pre-trained feature extractor to utilize it for its data set. So in here, we're focusing on learning the classifier head using frozen pre-trained feature extractors. So what I talked about here was for the centralized scenario where we have a server. But what about this decentralized case where we don't have a centralized server? So in that case, each client is responsible for aggregating and passing the knowledge, right? So this setup of GMMs can be also applied in that scenario, where let's say with each client, right, we already have our real features. Whenever we are getting a distribution from another client, let's call it a received GMM, we can just combine the synthetic features and real features and learn a new updated local GMM. So what I'm presenting here is the idea of like passing this GMMs and passing this parametric models in the network, right? And we aggregate the knowledge from the entire network. So I talked about Gaussian mixture. Now let's a little bit dive in a little bit what I mean by that. So we can use any parametric models, but in here we're using Gaussian mixture models or GMM as our parametric model. The reason we're using GMM is that GMMs are a universal approximate of densities, right? If you have enough mixtures, you can just describe any probability function, which was very cool about them. And the fact that they are very easy to estimate and work with and much more understandable was a perfect fit for us. So there won't be any math today, just very small ones. I show you why it's important to show here. So we can represent that each density function of a GMM by a set of tuples, right? So these are the parameters that we are passing to the network, right? Where I've talked about this pi is our mixture base, mu is our mean of Gaussians, sigma here represent the covariance, and K represents the number of mixtures. So the cool thing about this, if you think about it, we have two kind of flexibility in terms of number of mixtures and also how we represent this covariance matrix. It can be a full covariance matrix, diagonal, or spherical. Why that matters is that we are in federated learning and communication cost matters to us. So we want to be able to have flexibility in terms of how much communication we send. And therefore, like full covariance is has much more communication cost than, let's say, diagonal or spherical. Last thing, before we get to the results, is that we care about privacy. And like the thing is that we saw in papers, like they assume that, okay, since we're in the federated learning, everything is private, which is not. We have to have formal privacy guarantees in order to assure privacy. So in this, we're gonna use differential privacy. So and it's very straightforward. In differential privacy, you either add a Gaussian noise or another function, but in here we're just adding Gaussian noise to our new add signal. So this way of adding noise, we make sure that these tuples that we're sending, these GMMs that we are passing to the network, are differential private. And this assures that we are in this formal definition of differential privacy. Okay, now we're ready to show the cool parts experiments. So for our experiments, we're going to use 8 data sets and 3 foundation models. We're going to compare both centralized and decentralized topology. And for our experiments in here that I'm going to show you today, we're going to only train the classifier head of foundation models. But for other experiments that we fine-tune the rest of the models, I refer you to that paper. So this is the summary of all the data sets and foundation models we use. We use both ResNet, VIT-based, and CLIP. In here, we're just focusing on vision models for classification tasks specifically. Okay, so now let's to the first setup. of our centralized federated library. So this is a classical setup of 50 clients. We are using Caltech 101 dataset, and we are using CLIP as our pre-trained foundation model. So this black line here shows the federated averaging before that. So x-axis represents our communication cost in terms of megabytes, and our y-axis is accuracy, right? So this line here represents federated average. The reason this is a line is because this is a multi-iteration process, right? So we can have multiple points doing this as we perform multiple rounds. As you can see that like federated averaging starts very slow because naive averaging, right, in the first shot, first iteration doesn't perform well. But as it goes up, it reached the performance of centralized. Centralized is our oracle where we assume we have all the real features at the server, right? At the same time, you can see that FedPFD, our method, and DP-FedPFD is very, very competitive with centralized, right? And even the DP version as well. We're going to talk about why is that. But you can see that like FedPFD is close to the centralized performance. But you can see that other one-shot methods do not work as well, right? Because how hard it is in this scenario. In here, I just have a couple of, like I just showed you here the federated averaging and 3 one-shot methods. But in the next slide, I'm going to show you additional benchmarks that we did with the same method. So in here, I'm adding more lines here. So these lines are for different multi-iteration federated methods like FedYoki, FedProx, and we're adding more one-shot methods. But the idea is the same, right? One-shot methods, current one-shot methods, without sharing this knowledge, do not perform as well as methods that utilize this pre-trained knowledge of foundation models. And at the same time, you can see like we're showing different kind of, let's say, choices that we had for the parametric models. For example, you can see having one mixture has less accuracy than having 10 mixtures. Or like using diagonal covariance matrix is better than spherical at the cost of communication cost. So in here, we're just showing the trade-off, but the idea is the same. This is the next experiment, which I think this is my favorite experiment, is in the linear topology, right? In linear topology, we have, let's say, 5 clients connecting in a linear manner, right? And in this one-shot setting, right, we have to transfer knowledge from client 1 to 2, client 2 to 3, 3 to 4, and 4 to 5. And there is only a one-way communication between them, right? And using the GMMs, we can do that actually. And this is the results for that. So you can see, for example, as we pass this GMMs to each client, right, we are accumulating knowledge towards this linear topology. And in the end, we're going to reach the centralized performance as if we have all the clients' data in one place. And this is a very, very cool experiment, and it shows the capability of these GMMs as just like transfer of knowledge in a ad hoc situation as they go past the clients and accumulate knowledge of each client. Last 2 slides is basically a discussion and analysis like on what is happening, why GMMs are working, and why is it actually private or not. So the first question is that how well do GMMs model feature distributions? So in order to figure out like how well they model feature distribution, we measure the accuracy gap between 2 classifier heads, one trained on real features and 2 trained on synthetic features of GMMs. So this figure shows the accuracy of different types of GMMs, and x-axis represent the number of parameters we need to transfer these GMMs. Interestingly, we find that as you add more mixtures, you're going to have better representation of the real features, right? And we're going to see a trade-off between number of parameters and the effectiveness of GMMs. And we showed that, hey, full GMMs are not communication efficient, but diagonal and spherical GMMs with 10 to 50 give us a very competitive edge towards raw features. And it shows that, yes, features extracted from the pre-trained foundation models does resemble a Gaussian, but not a perfect Gaussian. Last thing, which I think is a very cool experiments we did, was that we did a reconstruction attack on our federated language setup. So one way, if you think about it, is that we can just, instead of training this parametric models, training this GMM, we can just send the raw features, right? The reason we cannot do that is because of this. A user can reconstruct exact images, right, from the raw features, as you can see here. So these are 3 examples we're showing here. And when we are sending raw features from clients to the server, with the assumption, of course, an attacker can reconstruct exact images. But if we do the same attack on FedPFT or DP-FedPFT, you can see that the resulting images are not similar to our test images, right? And that is a very, very, very good news for us. That, hey, without having this DP mechanism, right, still just understanding this parametric models can protect our privacy. Okay, now just a conclusion and discussion. We're gonna have a discussion on feature works here. So in today's presentation, I presented FedPFD, a one-shot communication FL method that enables foundation models. Our work highlights the capability of private feature sharing methods for knowledge transfer with foundation models. We just wanted to show that, hey, we can utilize this pre-trained knowledge of foundation models in a private manner. And the third question, that this is something that I'm actively trying to figure out, is that how we can utilize this private feature sharing for LLMs. The result we talked about today were mostly focused on vision models, right? And that would be cool to understand how we can use it for LLMs. Okay, now, so right now you can use FedPFD in Flower baselines with just 2 lines of code. I provide the link here. And yeah, I had an amazing time creating this baseline with the Flower, and it was the most developer-friendly experience I ever had. And I learned so much from it. And I definitely recommend not only for beginners in Flower, Federated Lane, but also like for developers who want to start working on open source projects. I think this is a very cool platform. And yeah, I encourage other researchers to also put their baselines there so we can have formal a comparison between these baselines. And yeah, thank you so much for having me. If you have any questions, yeah, happy to answer.
That was great. Yeah, thanks so much. So if anyone has questions who is with us live right now, feel free. You can raise your hand in the Zoom thing, or ask a question in the Q&A thing of the Zoom. Or we do have the Flower Slack channel. So I'll take a look and see what questions I can see. I don't see any in the Zoom, but I see some in the Slack. I see there's a question saying, could you elaborate on the cases where this approach doesn't work? So you mentioned, I guess they're talking about at the end, you mentioned LLMs, and you've mainly, I guess from this question, you can imagine it's, so they sort with images. Did you run into some other cases maybe, and are they data dependent? Are they architecture dependent? Any comments on
Yeah,
that?
absolutely. Yeah, that's a great question. So one thing we notice is that like we are focusing here on the last layer of before the classification layer. And the thing is that we cannot do this for any layer of a network, because before the that's the one of the main limitation of this work, is that we can just use it for classifier head, because other layers have like there's a positional embeddings in them that we cannot just use a simple Gaussian. So this last layer before the classification, because the way these foundation models were trained on made it possible for us. Basically, they were separable. These labels were separable, so we can just learn a Gaussian. And one of the main limitation. And the second thing, as I pointed out, was the LLMs. Like, like this kind of area of like this image classification is much more straightforward than translating understanding the last layer of like a next word token prediction, right? Because we not only we have embeddings there, we have to figure out, but also like we cannot just learn a Gaussian for each label, right? So it doesn't translate very well to that setting. And this is something that I'm um, want to work on that to see how we can bring the same idea of like this knowledge of pre-trained models to send them more efficiently in Flower, in Federated Learning.
I see. Okay, cool. Interesting.
Yeah.
Very cool. Let me see. Oh, there's another question here. What's the intuitive explanation for why FedPFT is more secure? Is it primarily because of the low-rank nature of the model representations being shared, or is there something in FedPFT actively preserving privacy?
Yeah, that is another absolutely fantastic question. Yes. So the thing is that FedPFT, like any federated learning, including FedPFT, with itself does not have a formal privacy guarantee. That's why we went to DP FedPFT to have a formal privacy guarantee. But as you saw in the end, like that was surprising to us as well that it was private for this specific construction attack. Like they have to be very specific in terms of privacy that like we haven't like nothing is private until like you cannot prove privacy towards attacking because there may be another attack that like FedPFT is not private on, right? But the reason that we saw that hey in here was private was absolutely you're right. If this low rank nature, this encoding of towards this Gaussian mixture and resampling right from these mixtures allowed us allows the server to not be able to exactly resample the features from the sender. So we are just encoding it to a very low dimensional, low rank space that allows us to have this kind of cool behavior, not being able to reconstruct the exact features.
I see. Yeah, makes sense. Cool. I actually I had one basic question, which was in one of the slides, um, maybe a slide 20, you showed the DP version of this and the standard
Yeah.
version of this. Hey, this one. They're quite close in accuracy. Or actually on second look, maybe it's a decent gap. It's like 10% gap there. I was just wondering, DP is quite tunable. And so could you speak a little bit about how did you tune this DP where there's a bit of an accuracy gap? Is it, for example, the same tuning for which you later show these example images? Is it the same kind of intensity and settings of the DP, or is it different?
Yeah, for sure. Like the thing is that like we treat FedPFT and DP FedPFT are exactly the same. Like before we send it to the clients, the only difference is that in here after calculating the covariance, mixture weight and mu, right? We add the noise. So before that is the same. For I think I don't remember exactly the delta and the epsilon we used, but we just set fix the delta and we tested for different epsilons and we just reported the results. And yes, like the gap actually is kind of far, but it's way better than we expected. The reason was that this Gaussians, right? It turns out that we don't need to add too much. That's one of the things that I love about one-shot FL, right? In the multi-iteration FL, because you're processing data again during the training, right? You have to have a lot of privacy budget, right? But because we're in this one-shot setting, we just process the data once and we calculate the means. So that is why we're seeing a better utility trade-off for us because we just process the data once and we add the noise. Unlike like federated learning in iteration that we have to add noise every time.
I see. That makes sense. Okay, cool. So one last quick question, and then the question is, which decentralized network topologies have you used this work in? And is it only the linear topology you showed us, or there are other ones? Or can you
Yeah.
speak a bit
Um,
about that?
yeah, for sure. Then actually we tested multiple scenarios. I just showed you the linear topology because I thought that was the coolest one. The other ones that we did was based on two clients. peer-to-peer connections. Let's say we have user A, user B, and user A can only transmit once to user B. And actually, in there, we tried different types of heterogeneity in terms of label shift, covariance shift, and path shift. So you can think of like user A has, let's say, images of a car, and user B has images of foods, right? And it was a very pretty cool experiment, and we saw the same results. But that's absolutely a great point. This is something in the future we're gonna consider, like, let's say, a more decentralized topology, and have to read like what are the main benchmarks they're using for decentralized learning, and we're gonna compare on that regard as well, for sure. Thank you for the question.
Okay, awesome, awesome. Well, thank you so much. We're sort of a bit out of time for this segment, so I see another question, but I'm afraid we'll have to take it offline.
Yeah.
So please post your questions just in you can mail them to me or post them in the Slack, and I'll forward them along to Maddie. So again, thank you so much for the talk. Great stuff. Really interesting use of federated learning, and it shows how it can really be a powerful tool for us to build models of this kind and leverage the other tools that are around, such as these foundation models. So very, very nice.
Thank you, my pleasure.